Hey guys, I'm Ethan, and today we're going to walk through installing the FTC blocks programming onto the starter kit robot for the first tech challenge into the deep season. Alright, here we've got an assembled starter kit robot. I've already connected to the Control Hub's Wi-Fi network with my external USB card. Now I'm using this external card so that I can also connect to the internet with my computer. It's just a nice quality of life thing. The other way you can do that is just by connecting to the Control Hub with its USB-C port. That also lets you program it and be connected to the internet, which is super helpful when you're looking for documentation or just need to download some code. The first step in this process is that we'll go over to gobuilda.com and download that example code. Here we are on the starter kit robot's resource guide for this season, and we'll scroll down to the download section. Here we have our step file, we have our example code for Android Studio and OnBot Java, and we also have our example code for blocks. Clicking this link brings us to the GitHub page, and this is where we store both of those files. We also have some documentation here which you can read to go through the steps of installing this. Here we've got two files. One that is a .blk file, which is the actual blocks file we'll install on the Control Hub. The other file we have here is a PNG file. This is just a screenshot of the blocks code, and you can use it to reference what it looks like, but we don't need to download this file. We're really after that .blk file. We'll click on it and you'll see some code here. Well, this is not what it actually looked like once we install it on the Control Hub though. We're going to go ahead and find these three dots at the top right, and then click the download button. And this will grab that file and just download it to our computer. Now we need to go over to our interface where we've gone to the URL of that Control Hub, and you should see this blocks tab here you can click on. Now we just need to upload op mode. So we can click this upload button right here and choose the file from our computer. We'll go ahead and go to our downloads folder, click that file that we just downloaded, and click open. Now I can hit OK, and we should see this populate as an option on in our blocks interface here. Now after we've installed this, we see a bunch of errors in here, and this makes sense because we haven't configured this robot yet. We have a lot of code, and this code references names of motors and servos, but it doesn't specify what ports each of those motors and servos are plugged into. That is where we use the configuration file. That's a file you build on your driver's station, and it actually says, hey, I know that you're calling this servo this specific name. Here's which port on the robot that device is plugged into. Now this error message has a handy reference for all of the individual motors and servos that we're missing. So we need to go through and in the configuration file make these objects and tell our robot which ports they're all plugged into. So we have our intake and wrist servos. We also have our left and right drive motors and our arm motor. So we can go here on our driver's station, click the three dots at the top right, and click Configure Robot. All right, on this page we're going to click New. We're going to find the Control Hub portal and click the Control Hub. Here we have the main page that lists all the different kinds of devices that we can configure. So first we're going to work on our motors. We're going to click Motors, and in port 0 I have the left motor. So we're going to select this drop-down that says nothing, and we're going to select the Gobuilda 5202/3/4 series. And because this is our left motor, we're going to call this left underscore front underscore drive. And you can see the exact capitalization and spelling and everything of that in that error message that's pulled up on our screen here. If any of those are incorrect and you try to click that, build that code again, it's going to give you that same error, though hopefully you've got at least some of these in the configuration file. We're going to keep going through. We're going to select that Gobuilda motor again. This time we're going to type in right front drive. And our last motor is plugged into port 2, which is the left underscore arm. Now we can click Done because that's all the motors we'll need to configure. Next we'll move into the servos button here. Now here you'll notice on the Control Hub that I haven't plugged in these servos into ports that are right next to each other. That's because several of the ports on the Control Hub share a power regulator. So ports 0 and 1, 2 and 3, and 4 and 5, so pairs of 2, share one source of power, and that power supply can be overdrawn by just 2 servos. So one servo is really great. It can pull just about the maximum allowed by those pairs of ports. But if you put two servos on the same port pair, they can overload that port pair, that like supply regulator, and then have those servos turn off and then turn back on. So if you have servos that seem like they just die randomly, maybe try changing which ports they're plugged into. Here I've spread out these servos a bunch. So I have one servo on port number 1 and another servo on port number 3. So these are for sure on different port pairs, and they can take all of the current that each of these servos can draw. Here we're going to go to port number 1 and select continuous rotation servo. Now there are two servo options here, continuous rotation or just servo, and we have one of each on this robot. We have a continuous rotation intake servo and a standard wrist servo. Now we actually are going to use the servo programmer that you get with your FTC kit to change the mode of the servo. That actually makes it respond continuously instead of moving to a specific position. But this lets us use different code to refer to those. So a continuous rotation servo you set between 0, -1, and 1, and a standard servo you set from 0 to 1. So standard makes more sense if you're controlling a positional servo, and continuous rotation makes more sense if you're controlling a continuous rotation servo. First, we have our continuous rotation servo on port number 1, and that is our intake. And then on port number 3, we have our standard servo called wrist. Now I can click done again, and because that's all, we don't have any sensors plugged in, just motors and servos, that's all we need to configure. We can go ahead and click done a few more times, click save, and then name that config file. I'm going to go starter robot. We can click done, okay, and then our robot will restart to apply that configuration file. Now that our robot's restarted, we're going to click this blocks button up here in the top left, and then that'll bring us back to our main blocks page where we can go back into that op mode. Here we're going to see if we get those errors that pop up again, and it looks like we haven't. So I think we've got all of the different servos and motors that are created in this config file. Here we have our blocks window. Now here's where we can actually go and program our robots in blocks, and you can see that there are a ton of comments in here. I do really recommend going through and reading these. These are linked to specific blocks, and they explain what each of these do. So by default, I have them uncollapsed and they take up a lot of the screen. That's okay because they provide a lot of information here. Now, an important thing to note about blocks programming is that we're doing this in kind of the backwards way. Normally, if you add a device like a motor, a servo, or a sensor to your robot, and you want to program with it in blocks, you're going to add it to your configuration file before you program it in blocks. If you add a sensor to your robot and you haven't added it to your configuration file yet, you won't find the functions for that sensor in the blocks programming until you've added it to your config file. Here is kind of an exception because you're taking a file that we created for this robot and uploading it to your robot, which doesn't have those objects in the config yet. All right, jumping right in, here we have our main loop. This is what everything runs inside of. Now, the first two blocks we find in here are functions. These are blocks of code that we've created and that you can create for your own code that let you move a bunch of blocks outside of your main loop. Your main loop can get crazy long before too long, and this one's already pretty long. But if you have code that needs to run over and over again, and you can boil it down to just one function, you can make it a function and then move it outside. That gives you a lot of control over when things happen, and especially if you find yourself making the same sets of blocks over and over, making that one function is nice. Here we've primarily used it, because these both run only once, to move a lot of just tall blocks outside of our main loop to make that a little bit shorter. Moving into our set default positions function, we have a bunch of different variables that we're creating. So we have set an arm collect variable to this specific number. Let's move through these one at a time. The first one we find is our arm ticks per degree. This is important because we use our encoder on our arm. This encoder is a sensor that's built into the motor, and it tells your controller how far that robot's motor has moved. So if it starts in this position and this arm rotates up, that encoder is keeping track of how far it's moved, and there's a specific number of encoder ticks that happen for every move, for every degree that the arm rotates. In our case, that is this 19.79, goes on and on, and that's the number of times the encoder ticks for every 1 degree. Making this variable allows us to think about how far the arm has moved in degrees instead of in ticks, because ticks are pretty arbitrary and they don't feel very intuitive at all. So after we've defined that, we're going to move into a bunch of these variables. So this arm collect variable is a specific position that we want to set our arm to, and that is 250 multiplied by the arm ticks per degree. So when we ask our arm to collect, we know that it wants to move 250 degrees away from where it started. All of these encoder positions are relative to where you start the motor, so make sure you start it in the same place in every single match, every time you hit init and then start on your robot. Here we have this arm down with the wrist folded in so that you have a consistent landing spot, and it can be the same every single time. Here we have a few different variables that capture different positions. We have a variable to collect from using our intake. We have one to clear the barrier. We have one to score specimen, one to score samples in the low basket, one to attach our hanging hook, and one to winch up the robot. And these all hold a different number of degrees that are that target position. In this overall function, we are declaring these variables so that we can use them later. Later in our code, we don't want to say go to 250 degrees. We want to say, hey, go make the arm move to the position it needs to be in to collect. Move the arm to arm collect. It makes it so that our code is talking way more about what the robot is doing and less about some numbers that don't make a lot of sense off the top of your head. Alongside the arm positions, we also have our intake modes. So we have a collect mode, which sets our intake all the way on in one direction. We have our intake off, which sets to 0. And we have our intake deposit, which sets to half speed to shoot out. Now you can tune these as well. And then every time you call to turn on your intake to collect, you can use that changed number. So if you want to make your collection just a little bit slower, or if you want to make your deposit a little bit faster, you can change that in one place and it'll take effect everywhere in your code. Similar story for the wrist positions. We have our wrist folded out position, which is at 0.5, and our wrist folded in position, which is 1/3 on top of that, which is 90 degrees for this particular servo. We also have our fudge factor, which we'll get into in just a little bit. Now the next block we run into in our main loop is set motor settings. Now this is down here. And this sets a lot of the particular settings that we like to use for motors. It sets the brake mode to on, so it makes it so this robot stops a lot faster, and it makes the arm have a better chance at staying upright. And this is nice because I think it just makes the robot feel more controllable. The other thing it does is it sets a current limit alert, which we'll also talk about in just a little bit, and it turns our arm motor into the run to position mode. That run to position mode is the method that we use to use that encoder to drive the arm to a specific spot and have it stop and stay there. It's really nice that we can command the arm to move to a position, and even if the load increases or decreases, it's going to apply the perfect amount of power to stay in that position. Now we're getting into more of the meat and potatoes of this code. The first thing we're going to do is we're going to set our intake power to off. Just make sure that our intake is off, and we're going to set our wrist to fold it in. Now both of these happen before you click start on your program, but after you hit init. All right, now we have the more required blocks. So call wait for start, waits until you click that start button, and then while op mode is active, and this is the section of code that repeats continuously until you click the stop button at the end of our match. The first thing we're going to do is set our drive motor power. So we set our front left drive and our front right drive to these specific variables that are related to the gamepad. So the gamepad left stick Y plus the gamepad right stick X is the exact power we should set to our front left motor. Now this lets us control it in a skid steer or a tank style, arcade style, where if you push this joystick forward, both motors drive forward. If you push the right stick left, both motors go in opposite directions to make your robot turn left. So it's a very intuitive way to drive the robot. It just is a little bit more complicated to code. The next thing we run into is a set of if-else statements. So we say, hey, if the gamepad's button A is pressed, then we want to set our intake to collect. We turn it on, and that sets that to that variable that we declared earlier. Now, inside of that else statement, so if the code first checks to see if gamepad A is pressed. If it hasn't been pressed, well, now we can check and see if gamepad X is pressed. This stops somebody from clicking both of these buttons at the same time and having that servo bounce between trying to set two different positions. If you're holding the button A, then it's not going to check if X is pressed, and it isn't ever going to try to set the next thing. And we do that a lot just to make sure our code is a little bit safer if somebody accidentally clicks multiple buttons. So the next thing we have is gamepad X turns the intake off, and gamepad B turns the intake to deposit. The next part of our code is our arm position fudge factor. Kind of a long name, but what it lets us do is adjust the position of the arm just a little bit in case something is just out of reach or you need to fudge the arm up and down. That's with the gamepad's triggers. So we set our gamepad fudge, our fudge factor needs to be multiplied by the right trigger plus the inverse of the left trigger. This means that when you pull the right trigger, the arm will go up just a little bit and the left trigger goes down a little bit. But this keeps the overall position of the arm the same. As soon as you let go of those triggers, it goes back to that exact programmed position. The next bit of code is a lot of if-else statements because these all have to do with controlling the arm. If we click the right bumper on our robot, we want to move the arm back to the position it needs to be into intake. We need to then fold out the wrist and turn on the intake. Now, some of these things might already be true when you click the right bumper. The intake might already be on, or the wrist might already be folded out, and that's okay. We want to make sure that every time we click the right bumper, that arm goes to a consistent position because we know the driver is ready to intake something. I like thinking about programming this way because we're trying to make these buttons really simple for the driver. That's gonna be how we make the most effective robot, is if we can make it easy to drive. So if you know every time you're ready to go collect something, you click one button instead of having to move the arm and then fold out the intake and then turn it on, we can save some steps. And through the rest of this bit of code, we have a lot of similar stories. If you click gamepad Y, it's gonna move to score the sample in the low basket, and it's also gonna fold in score the sample in the low rung. It's also going to fold in the wrist because we know we need to change that wrist position in order to score a sample. Going through the rest of this code, we see a lot of very similar setups. If we click the left bumper, we're going to move that arm up just a little bit, kind of regardless of what the intake and the wrists are doing. If we click that left bumper, it's going to bring up the arm to that arm clear barrier position. If we click D-pad left, it's going to move to collapse the arm in the robot, it's going to turn off the intake, and it's going to fold in the wrist. All of this stuff is really intuitive and easy to read, and a lot of that is because we've made these variables that say what the action should be. They contain a number, but that number doesn't make any sense. But the name of that variable can make a lot of sense. So it's easy to refer to it in different ways, and it's easy to look at this and understand what the robot's trying to do. Now, here we actually set the arm motor to a target position. So here we only set that target position once. In each of these if-else statements, we aren't setting the target position. We're waiting until we've gone through everything. We found at the end of that loop, what do we want to set that arm motor's target position to? And we're going to set that to the arm position plus the fudge factor we talked about earlier. So having those two variables go together, where the fudge factor can adjust the variable that's being set to the arm, is how that fudge factor actually works behind the scenes. Then we're going to set that run mode to run to position, and we're going to set the velocity to 2100. This is the maximum speed that the arm motor can go at, and if you want that arm to go slower or faster, you can increase or decrease that number. We also check and see if the motor is over current. If the motor is stalling, if it's hitting an end stop and can't move, it'll show a sudden telemetry on our driver hub, which will alert the driver and say, oh hey, that arm motor is doing something that it shouldn't be doing, and it might be getting really hot. The other telemetry we print is, and that's going to show up on the driver's station, is the arm target position and the arm current position. This is kind of a helpful debugging tool. If you see that your arm just goes crazy, then it might have, the encoder direction might be wrong. You may have called it a different motor in the configuration file, or the polarity of the motor might just need to be reversed. So that's a troubleshooting aid that can kind of help us work through and solve problems with how the arm works. And then the last block here is the telemetry.update that will push all of those new telemetry numbers that we have created in our code to the driver's station from the robot. Now that we have uploaded our code and taken a few minutes to digest how it works, we can go ahead and start testing it. Now, because the motor's encoder is relative, we need to make sure it starts folded in. So we're going to fold our arm in, we're going to fold our wrist in, and we're going to set it against this base plate. Now, on our driver's station, we can click this right drop down. This is where you'll find the tele-op, or the driver-controlled part of this, and you see that code that we just uploaded. We can select it, and that'll pull that up, and we're ready to hit this init button. This init button gets our robot ready to run. We can click it, and what it'll do is run any blocks that exist in our code before that wait to start block and that while op mode is active loop. In our code, this initializes those servos, it creates those variables that we needed to create, and it turns on the motors. So it sets those to brake mode, and you can see that they are just harder to rotate already than when that op mode is not enabled. We can initialize it, and this is where you'll be when you're getting started and ready for a match. We can click this start button, and an important note here is that I have this robot up on blocks so that the wheels can rotate and I'm clear of the way of any degrees of freedom, like the arm on this robot, so that if it does something that I'm not expecting, I'm not going to get hit by it or hurt in any way. The first thing I want to check is our drivetrain. Both of these wheels should go forward when I push the left stick forward, and they all do. So the right side of the drivetrain goes forward, the left side of the drivetrain goes forward. If I pull it backward, the robot would go backward. When I push this right joystick to the left, we should see the left side go backward and the right side go forward, which would rotate this robot around its center. Now you can do combinations of these to do different motions when you're actually driving this robot around, but those are the key parts. Now we can look at other components of this. The first thing that we're going to test, we're going to hold the robot down for this, is we're going to test the arm, the wrist, and the intake by clicking the right bumper. This will go to the position it should be in to intake, and it sure does that. We can see that we don't have the current alert show up on our driver's hub. We can see our current position and our target position are really close, and our intake is turned on and our wrist is folded out. We can also test our triggers, so these will fudge the position. So we can lift that arm up just a little bit with the triggers. We can then click the Y button, and that'll move that arm up to a new position, and we can change that position with those triggers. We can fold that arm in, it'll turn off the intake and fold it in the wrist, and we're back to where we started. That's just one of those buttons. That's my favorite part about this code, is that it breaks up a lot of complex parts of driving your robot into one button that you click that does multiple things. It makes it really streamlined, and it just takes a little bit more thought when you're setting up the code. Now we can go ahead and click stop as we have finished verifying that our code all works, and we're ready to make modifications and make this code our own, or work on this robot and improve it. If you have questions about this or other parts we sell over at gobuilda.com, shoot us an email to tech@gobuilda.com.